Greetings, AI practitioners. Understanding generative models demands a solid grasp of neural networks. This session offers a concise, targeted refresher. Deep neural networks are powerful because they learn meaningful, hierarchical representations of the input data, not just raw features. Early layers capture simple features like edges. Deeper layers combine these into increasingly abstract concepts like object parts or entire objects. This final, compact representation is often termed the latent space. It acts as a compressed, semantic blueprint of the input data. In generative models, manipulating or sampling points from this latent space allows us to create novel, coherent, and diverse data instances. CNNs excel at processing grid-like data, particularly images. They leverage specialized layers to detect local patterns and spatial hierarchies. The core of CNNs is the convolution operation. A small filter, or kernel, slides across the input, performing element-wise multiplications and summing. Each unique filter generates a feature map, highlighting where a specific pattern, like an edge or texture, appears in the input. Pooling layers, typically max pooling, reduce the spatial dimensions of feature maps. This reduces computation and makes features more robust to small shifts. A typical CNN stacks multiple convolutional and pooling layers, gradually transforming raw pixels into high-level conceptual features. CNNs are fundamental to image-generating models, from GANs and VAEs to diffusion models, enabling high-fidelity visual synthesis. We'll cover artificial, convolutional, and recurrent neural networks, exploring how they learn complex representations and the mechanism of backpropagation. RNNs specialize in sequential data, where the order of information matters. Think text, speech, or time series data. Unlike ANNs, RNNs have a recurrent connection, allowing information from previous time steps to influence the current output. This gives them memory. The hidden state, updated at each time step, encapsulates the network's understanding of the sequence processed so far. It's the short-term memory. Conceptually, an RNN can be unrolled into a sequence of ANNs, each handling one time step and passing its hidden state forward. The fundamental unit of a neural network is the artificial neuron. It mimics biological neurons by processing signals. Each input is multiplied by a learnable weight, determining its importance. A bias term is added, shifting the neuron's activation threshold. The weighted sum then passes through an activation function. This crucial nonlinear transformation allows networks to model complex relationships. Early networks often used sigmoid, outputting 0 to 1, or tan, ranging from -1 to 1. These are useful for probability outputs. Rectified linear unit, or ReLU, is now the standard. It outputs the input for positive values, otherwise 0, effectively addressing vanishing gradients. An input layer, one or more hidden layers, and a final output layer. During the forward pass, input data propagates through each layer, undergoing weighted sums and activations to produce the final output.